Hello, and welcome to another science post. This one is on quantum mechanics, and it's called the exclusion principle. The first step of every young person's quantum mechanics education is to define intuition as a foolish way of thinking ruled by emotion instead of reason. This straw man must first be destroyed before embarking on the so arduous and abstract journey to the higher mysteries. Just like those students of philosophy who have accepted Hume's insight that it implies no logical contradiction that the sun will not rise tomorrow, students of quantum mechanics who survive the journey to the safety of tenure will not be bothered by the fact that Schrödinger's cat has become a zombie in a superposition of states, dead and alive. Nor will they be bothered that in the quantum realm, barring an incantation of the Pauli exclusion principle, I could walk over and occupy the same space as you at the same time and in the same way. Those students will eagerly acknowledge that the math of quantum mechanics does not commute. They will throw away the Boolean logic that powers their computers and embrace a world where A times B is not equal to B times A. They will be mystified by this fact and have no intuitive reason for accepting it. Yet, in order to be accepted by the group of physicists, they will repeat it as gospel. After gaining some time and space from my days as a student, I conclude that these features of quantum mechanics are a result of a deliberate limitation of our perspective in order to make the math easier. You have to put blinders on your horses in order to keep them from spooking in the face of mental shortcuts that detach them from their intuition. Certainly, waves like light can be in a superposition of states, but particles? If particles had no trouble being in a superposition of states, then we wouldn't need to invoke the Pauli exclusion principle so often. Ignoring the fact that a wave may seem to act like a particle when it can only ever be measured with particles, and a particle may act like a wave when it can only ever be measured with waves, intuition is confused and old definitions are blurred when quantum mechanics defines two types of particles, fermions and bosons. Fermions usually act like particles, but sometimes act like waves, and bosons usually act like waves, but sometimes act like particles. Don't we love mixing up our definitions and creating unnecessary redundancies? It makes certain mathematical calculations easier, so who cares if we completely throw our intuition in the trash? Concrete concepts get mixed even further through discussions of wave packets and the wave function of an electron. Students are assured that thinking of the electron as a wave is better than thinking of the electron riding on a wave or an electron propagating like a vortex with a wake. Finally, we have the introduction of three redundant and blurred definitions of spin and charge, or what the charge and angular momentum of the particle mean. We have spin, an abstract concept that should not be confused with our common notion of what a spinning object is, weak isospin, and antimatter. Upon closer inspection, these are three ways to say basically the same thing. Back in the good old days, we used to develop intuition with more fluid mechanical concepts. like vorticity. For example, if you freeze a sphere of rotating liquid, the angular velocity of the solid is half of the liquid's vorticity, and this would provide an intuitive explanation for the G factor, the ratio between the magnetic moment and the angular momentum. It gives you an intuitive understanding of the concept of spin. But quantum mechanics has no use for such ways of thinking. They prefer mixing things, making them a little less clear in order to develop estimates of quantities that are hard to estimate in other ways. Things get even more opaque when electron degeneracy pressure is introduced as a fact of nature with no discernible cause, even though most quantum mechanics curricula do not teach this. The electron degeneracy pressures within an atom can be understood intuitively and calculated from first principles. The pressure can be literally thought of as a pressure. These equations were developed back in the 1800s by a student of Hertz named Bjerknes. Actually, it was his father, Bjerknes' father, and these equations were further developed in the 1980s by a Russian physicist named Zabolotskaya. Both of these people studied the physics of bubbles in vibrating liquids. The pressure gradients of the ground state of an atom are quite easy to calculate with their equations, but it is more difficult to derive analytic expressions for higher orbitals because of the probabilistic nature of things. A parallel, yet independent way of calculating pressure gradients is derived from the work of August Sommerfeld from 1868 through 1951. That's when he lived. And he was the doctoral advisor to the fathers of quantum mechanics, all of those famous names you know, Heisenberg, Schrödinger, and so on. In 2 dimensions, such systems are much easier to describe, and those equations are much older than the fathers of quantum mechanics. For example, the Chladni plate reproduces the 2-dimensional patterns of the atomic orbitals, and it has been studied and characterized since the dawn of civilization. Even Leonardo da Vinci wrote about Chladni plates. But the most elegant mathematical description that has made it through the bottlenecks of history is that of Sophie Germain, a woman who lived in the 1700s. And she was in contact with a famous physicist named, you might know his name, Gauss. One might compare her work on the Chladni plate to the solution of the Schrödinger equation in 2 dimensions. And in my blog post, I have some nice videos on this. Something you really have to see to understand. It is important to note that in Sophie Germain's time, the solution to the Schrödinger equation, or the quantum mechanics as described by Hilbert space by modern physicists today, it would have been viewed as an approximation of how a system undergoing a constant acceleration or vibration will behave. Accordingly, it is rather stupid to expect objects in a vibrating system to behave like objects in a stationary system. But that is what we are doing when we find quantum behaviors like entanglement mysterious. People from the past, like Sophie Germain, would not have found this mysterious at all, and I blame pop scientists for mystifying things in order to engage the public's sense of wonder and try to get them to give them their money. The sorts of outstanding problems in the quantum realm are expressed in a language that takes a lot of time to master, at least the language they use at the graduate level. It's practically like a code. And this excludes a lot of people from taking part in the discussion. I've often wondered if that is what exclusion really means in the Pauli exclusion principle. In order to be more inclusive, I am going to try to use plain English to explain these things. Sometimes the result is quite comical, as when I try to solve the Yang-Mills mass gap problem in colloquial language and fail to win the associated Millennium Prize. What I'm trying to do with this is show how people gain power by using strange language that if you reduce it to something more sensible, they're really expressing very simple ideas. So, the Yang-Mills mass gap problem, which if you solve it, you win $1 million or something, is that you have to prove that for any compact simple gauge group G, a non-trivial quantum Yang-Mills theory exists on R4 and has a mass gap delta greater than 0. Existence includes establishing axiomatic properties at least as strong as those cited in Streeter and Whiten from 1964 or Osterwalder and Strader from 1973. Yang-Mills theory, I have to break this down into pieces. Yang-Mills theory describes the unification of the electromagnetic force and the weak force, the force that causes the electrons to orbit around a proton and the force that causes a neutron to decay into an electron and a proton. This is like the difference between a moon that spins as it orbits a planet and a moon that is tidally locked or not spinning as it orbits a planet. The force that holds the moon close to the planet is the same regardless of the moon's spin. That is what is meant by unification, showing that the same force is behind two seemingly different things. And that is what that's what Yang-Mills theory did with protons and neutrons and electrons, where they became, I guess, confused that on the quantum scale, they don't seem to act like little planets when you blur your definitions of particles and waves. So, the theory is written in non-abelian Lie algebra, essentially gibberish that a small subset of people pretends to understand. And it's not something that has a lot of useful applications. I like to mispronounce these words and call it a non-abelian Lie algebra and say that if you are not able to understand that it is a lie, then you are not smart enough to join the club. This is what is really meant by Pauli's exclusion principle. So at this point, I'm going to sort of become rather snarky, but at the same time deliver this in a deadpan manner. So I'm going to be translating strange technical terms into terms that are easier to access, and I'm trying to be a bit facetious. So don't feel too confused if you're not sure if I'm joking or not. So, the Yang-Mills theory was written in non-abelian Lie algebra, and the mass gap problem is to prove that there is a minimum change in mass that can occur in nature, and the bit about Osterwalder and Schrader refers to axioms for Euclidean Green's functions, rules for how to add together fields, which are a fancy way of saying forces. So notice how you have to translate layer upon layer to get to something that people understand. People understand what a force is, but most people don't know what a field is. And how simple is it just to say a field is the same thing as a force? And axioms for Euclidean Green's functions are referring to fancy ways to add together, or rules for how to add together forces. And in plain English, these rules boil down to fields add together when they overlap, something rather simple. This means that the solution to the problem should be given in terms of fields that add together when they overlap. Okay, that's translated one part of the millennium problem, of the mass gap problem. And now I'm going to break this up into 3 approaches to solving the problem, to illuminate the 3 different sort of schools of thought. Instead of trying to find a colloquial way to say, like a mathematician, I am applying a Galerkin method to convert a continuous operator problem into a discrete problem, I will try to speak in the language of physicists instead. So the physicists have rejected the mathematician's language, and so we're going to try to solve the problem in the language of physics. Approach A. It seems like the solution to the mass gap problem should be trivial, since the uncertainty principle describes a minimum momentum change allowed over a certain distance, or a minimum energy change allowed over a certain time step, and holding velocity constant results in a minimum mass change allowed over a distance or time step. Zeno's paradox allows us to put a limit on a minimum distance step and time step, and that in turn puts a limit on a minimum mass change. But this answer is not given in terms of fields, so we have to try another approach. This will be approach B, a more geometric approach. You can fit an infinite number of lines in a space, but only a finite number of circles, and this means that fields in a line can be infinitely large or small. But when a maximum number of circles is crammed into a finite space, these circular fields necessarily have a minimum size, and that will correspond to a minimum mass. Problem solved, since mass is defined by circulating and linear motions. But maybe the judges wouldn't accept this language because it's too geometrical. So I'll try a third approach that they might accept. To solve the mass gap problem in the overly complicated language of fields, a few heuristics must be introduced. Per the original interpretation of the Laplacian, the gravitational field is caused by a linear breathing motion of an object, which is proportional to the energy or mass contained within the object. Per the equipartition theorem, this energy is made up of equal parts rotation and linear motion. An electromagnetic field is caused by rotational and linear motions that are perpendicular to and out of phase with the fluctuating pressure or breathing motion driving gravity. Something that people in the 1700s and 1800s would understand perfectly yet which would mystify a large number of physicists today. This is worrisome. Because these motions are out of phase, gravitational and electromagnetic fields are constantly exchanging energy. All of these electromagnetic circulating motions in an atom are taking place at multiples of a characteristic velocity, defined by the speed of light multiplied by the fine structure constant, and this velocity defines the size of the system with a given mass because it defines the amount of time it takes for a stable orbit to occur. It is helpful to visualize a clock. The second hand is the subatomic realm, and it moves around at the speed of light. The minute hand is the atomic realm, moving at the speed of light times the fine structure constant. And the hour hand travels at the speed with which the universe seems to expand, a value that is close enough to half of the speed of light times the fine structure constant squared. That I bet there is a pattern here. With such a pattern in the subatomic realm, the hours on the clock are given by the 30-degree Weinberg angle and can be expressed in terms of the electric charge's coupling constant. Weak hypercharge and weak isospin, where isospin describes the degree to which the spin of a thing is lined up with its direction of motion. It took me quite a while to untangle how spin and isospin and all of these overlapping definitions all work together, and I think they've just created a mountain that students have to climb in order to join a club, which is not very worthwhile. It's a scam, I think. The view from the top of the mountain is maybe not worth seeing, or once you get there, you may wish that you had not been so changed by your journey, something like that. This all leads to some very weird stories about things that virtually exist by temporarily violating conservation of energy or traveling faster than light. There is also something called the Eightfold Path, and I'd rather not fall down that rabbit hole, unless it is in the context of morality rather than physics. Looking back at these three different approaches, I think I was doing better with the first two. I think this last approach, which is more in the language of standard model type physics, it went off the rails. Chalk is ipso facto cheaper than gray matter. QED. Did I win the Millennium Prize? May I have $1 million now? I beg your pardon. I didn't use the right language. Oh, pity. But if the language is what is standing in the way of a solution, maybe the language is the problem. Okay, that's enough of my snark. It's annoying, I know. I'm a rather silly person who gets annoyed with abductive reasoning and prefers the deductive language of bubbles springing from the vacuum. And I encourage you to click on the link to the blog post. There are some nice videos of some physical systems that motivate that sort of heuristic. I first posted this material on Quora, and I'm compiling my science writing into a 2-book set. But instead of editing that work, I am procrastinating by blogging and making these videos. Maybe I'll be able to publish that book in a few months. I mean, if I really get to it, I can finish it. It's not like writing fiction, where fiction, you can do whatever you want, but if you're writing science, it really has to be right. It's a bit more work, I find. Until then, the only long-form work I have published is in the form of fiction. That is safe for kids, but interesting for adults. So far, I've gotten my most positive feedback from rather older men. So, I don't know, there's something in it that's worth reading, I think. I'm going to go take a break from making videos and make some soups, or eat some soup. I made some really excellent soups yesterday. One was a nice borscht, and with a really good stock, and the other one is a 5-onion creamy soup, which is so oniony in so many ways that it's wonderful. Until next time, thank you for watching, and please tune in for my future videos.